Hello everyone, this is lecture 23, the cross product. So in the last lecture, we get to work with the dot product of the two vectors. The result of the dot product is going to give you a number or a scalar, therefore it's also called the scalar product. In this lecture, we'll look at a different product, it's called the cross product, and the result of the cross product of two vectors is going to be another vector. And therefore, another name for the cross product is called the vector product. I'm going to give you two different techniques to obtain the cross product of two vectors. One that we're going to cover in the first part of the lecture, and another technique we're going to use for us to use the determinants to calculate the cross product, which is covered toward the end of the lecture. So let's start with the definition. If you have two vectors, let's consider the three-dimensional vectors. So if u equal to u1, u2, u3, and v is equal to v1, v2, and v3 are vectors in R3, then the cross product of u and v is the vector defined by the following formula. So you have the notation of u crosses with v. So this particular notation right here is to indicate the cross product of the two vectors u crosses with v. Right. And for the cross product, the way or the order on which you write the vectors matters, right? Because unlike the dot product, when the dot product is commutative, the cross product is not commutative. So therefore, if u is on the left of the cross product, it has to stay on the left, v has to stay on the right. And if you swap the position or the order of the vectors, you will have a different result for the cross product. And the cross product of u and v is going to be equal to u2 v3 minus u3 v2, comma u3 v1 minus u1 v3, comma u1 v2 minus u2 v1. And this, because the cross product is a calculations from a three-dimensional vectors, then the result is also a vector in 3 dimensions. And you don't have to memorize this particular formula. There's some way that we can actually calculate the cross product without memorizing the formula, this particular formula right here. I'm going to give you a technique to obtain this formula, and later on when you use the determinant to calculate the cross product, it's going to be very simple to get. All right, so instead of memorizing the formula, what we're going to do is from these two vectors, we're going to form a 2x3 matrix. So instead of memorizing formula, we can obtain the component of u crosses with v as follows. All right, so first, as I mentioned, you're going to form a 2x3 matrix. All right, so the matrix is of the form u1, u2, u3, and the second row is v1, v2, v3. So you have the components of vector u on the first row because u is on the left of the cross product, right? Or the first vector in the cross product, and v is in the second row because v is the second vector in the cross product. If you swap the positions of v and u in the cross product, if you do v crosses with u, then the component of v has to be in the first row and the component of u has to be in the second row. But in this case, you have the order that is u crosses with v, so therefore the components of u is in the first row and the components of v is in the second row. All right, so after forming a 2x3 matrix, what you do to get the first component of the cross product is to remove the first column and then take the determinant of the remaining matrix. Okay, so what to get the first component, you do is you remove the first column, then take the determinant of the remaining matrix. All right, so that is going to take the determinant of u2, u3, v2, v3. All right, so to get the first component, you remove the first column here, and you take the determinant of the remaining matrix, right? And the determinant is going to be u2, u3, v2, v3, and this is the 2x2 determinant, so you can do the calculations fairly easily. First, to get the second component, you remove the second column, and you take the negative of the remaining matrix, right? Or just take the negative of the determinant of u1, u3, v1, and v3. So here for the second component, I'm going to remove the second column, and the remaining matrix is going to be u1, u3, v1, v3, and you take the negative of the determinant of that. To obtain the second component, remove the second column and then take the negative of the determinant of the remaining matrix. So that is, take the negative of U1, U3, V1, V3. And of course, for the last component, what you do is you remove the third component of the cross product and then take the determinant of the remaining matrix. So in this case, again, you remove the third column when you want to calculate the third component of the cross product, and by taking the determinant of the remaining term. So for the third component, we find the determinant of U1, U2, V1, and V2. And that's how you obtain the components of the cross product of the two vectors. Now let's do the calculation for a particular example. So given two vectors, two three-dimensional vectors, U is equal to -1, 2, 5, and V is equal to 4, 0, -3. Can you calculate U crosses with V and then V crosses with U? So as you can see, the order on which you perform the cross product is going to matter in these calculations. All right, so for U crosses with V, because U is the first vector in the cross product, so when you form from here, you form a 2 by 3 matrix. So what you do is you have -1, 2, 5, and then V is the second vector in the calculation or in the cross product. So you put the component in the second row. All right, so you form a 2 by 3 matrix. Now the cross product going to be equal to, this is a 2 by 3 vectors because you have two three-dimensional vectors, right? So therefore, you have the results going to be a three-dimensional vectors as well. So for the first component, you remove the first column and then take the determinant of the remaining value or the remaining matrix of 2, 5, 0, -3. For the second component, this is 4. So for the second component, what you do is you remove the second column and then take the negative of the determinant of the remaining terms. So negative of negative, determinant of -1, 5, 4, -3. And for the last component, you remove the last column and then take the determinant of the remaining term, -1, 2, 4, 0. And the results you can see is a three-dimensional vectors. These calculations are the 2 by 2 determinants. So it's very straightforward for us to do. So 2 times -3 minus 0 times 5, get -6 for the first component. And the second component has to be 17, positive 17. And the last component is going to be equal to -8. If you do the calculation correctly, this has to be the result. All right. So for this example, it's also asks you to calculate the cross product of V and U, or V crosses with U. As I mentioned earlier, the order on which you do the cross product matter. Right? So in this case, V is the first vector in the cross product, and U is the second vector in the cross product. So therefore, when you form a 2 by 3 matrix, you should have 4, 0, -3. This is -1, 2, 5. And the cross product V crosses with U is going to be equal to the first component. Again, remove the first column and take the determinant of the remaining terms. You have 0, -3, 2, 5. Now for the second component, what you do is you remove the second column, then take the negative of the determinant of the remaining terms, so the determinant of 4, -3, -1, 5. And for the last component, you remove the last column and then take the determinant of the remaining term of 4, 0, -1, 2, 1. And if you do the calculations correctly, you should have 6, -17, and positive 8. And as you can see, the result of these two cross products are different, right? So you can conclude from these calculations. So this calculation shows that U crosses with V is different from V crosses with U. More specifically, you have that U crosses with V equal to negative of V crosses with U. So that means when you switch the component or the order of the vector in the cross product, you obtain the opposite result of the original cross product. Okay. So let's do a similar calculation. U crosses with V and then V crosses with U. Okay, so in this case, you also have two three-dimensional vectors. When you do U crosses with V, So we form a 2 by 3 matrix of the form 0, 2, 1, and V is 3, negative 1, 0. Again, you have the setup because U is the first vector in the cross product and V is the second vector in the cross product. Now, for the component of U crosses with V, it's going to be equal to the determinant of 2, 1, negative 1, 0. The second component is negative of 0, the determinant of 0, 1, 3, 0. And the last component is going to be the determinant of 0, 2, 3, negative 1. And the result you get for this calculation is 1, 3, negative 6. And as we see in the last example, is that when you do U crosses with V, that's going to be equal to negative of V crosses with U and vice versa. So when you do V crosses with U, it's going to be equal to negative of U crosses with V, or negative of the vector 1, 3, negative 6. And therefore, the result of V crosses with U is negative 1, negative 3, and positive 6. That's one way to find the value or the vector of the cross product. We have another technique, is more practical, is more widely used in mathematics, physics, and in other sciences to calculate the cross product of two vectors. So before going into that particular technique, I want to touch on the properties of the cross product. As you can see, it's going to be slightly different from the properties seen for the dot product. So for the properties of the cross product, also let's consider three different vectors, U, V, and W. And let's say you have a scalar C in this case. And the first property is similar to what we see in the last two examples, is the anti-commutative property. That is the order on which you have the cross product matter. So U crosses with V is going to be different from V crosses with U. And therefore, you have U crosses with V equal to negative V crosses with U. Now, moving on to the second property, this is called distributive property. As I mentioned in the last lecture, distributive property for dot product will be different from the distributive property of cross product because the order on which you do the cross product matter. Right? So the cross product on the left cross product and the right cross product is going to be different. So what do I mean by that? When you do U crosses with V plus W, because U stay on the left of the parentheses, right? When you do the distributive property, U always has to stay on the left of the vectors. So of the cross product. So U crosses with V because at the beginning you stay on the left of the parentheses. So here, when you do distribution, U has to stay on the left of the cross product plus U crosses with W. Now, instead of the left cross product, you do right cross product. That is V plus W crosses with U. Now, U stay on the right of the cross product. When you do distributions, you have V crosses with U plus W crosses with U. Right. So you have to be careful when you do distributive property for the cross product. Now, for multiplication by a constant, what you have is C times U crosses with V is going to be equivalent to doing when you scale the vector U first and then do the cross product with V, or you scale V first and then do the cross product with U later. So this statement are equivalent to one another. When you do the cross product with a zero vector, you're going to receive a zero vector. At the end, the result has to always be the vector, right? Because it's the cross product, it's another name for that. It's called the vector product because the result is a vector. Whereas in the dot product, the result is a scalar. So it's called the scalar product. For the last property here, the cross product of a vector with itself is going to be, so U crosses with U equal to a zero vector. Right? So its crosses with itself is going to be equal to 0. Sometimes it's very useful to know the cross product of standard unit vectors. If you consider the three-dimensional case, the standard unit vectors for three-dimensional coordinate system is I, J, and K. Right? So I crosses with itself, right? It's going to be equal to the 0 vector. Right? So we can take this fifth properties of the cross product and apply it in here. Now, for the case in the y direction, you have J hat crosses with itself. It's going to be equal to 0. K crosses with itself is going to be equal to 0 vector as well. Now, there's the relationship between I, J, and K when you perform the cross product. And I'm going to use this particular circle to help us memorize the cross product between I, J, and K. So I hat crosses with J hat is going to be equal to K hat. So let me start with I hat here. This is J hat, and this is K hat. Right. So I crosses with J, it's going to give you K. Right. So in the positive directions, when we go to the negative direction, that will indicate that. So I crosses with j will give you k. J crosses with k will give us I. And then k crosses with I will give you j. Okay, so that's the positive directions. Right, so here positive, here positive. Now, if we go the other way, right, so if you do j crosses with I, it's going to be equal to negative k. So j go the other way. J crosses with I, I'm going to give you negative k. K crosses with j, going to give you negative I. So you go the other way here, negative. And when you do I crosses with k, will give you negative j. So next we have example 3 and example 4. So in this two example, we're going to be able to use the relationship between these and the unit vectors in the cross product to calculate the following statement. So you have I crosses with j crosses with k. So let's do j crosses with k first. Now you go back to here, you have j crosses with k going to be equal to I. So I crosses with itself give you a 0 vector. Okay, that's simple, right? So very straightforward. Now you have a I crosses with j, then k crosses with I. So let's do the cross product inside the parenthesis first. So I crosses with j give you k hat, and k crosses with j give you with I give you j hat, and then k crosses with j is going to be negative I. Right, so straightforward. Okay, so now we're going to move on to another application of the cross product is to see the relationship between cross product and the dot product. In this theorem, it's going to look at two calculations or two statements instead of 5 like this. So I'm going to cross out C, D, and E. At the beginning, I thought I planned for 5 different properties, but I decided just to show you 2 properties that connect the cross product and the dot product together. Now, to see this property or this relationship, what you need to understand is that when you have 2 vector, let's say U, vector U, and a vector V like this, and when you do the cross product will give you a new vector. This new vector is perpendicular. So this new vector U crosses with V is perpendicular to both U and V. And when you have 2 vectors that is perpendicular together, or they form a right triangle, by the dot product of the 2 vectors formed with the right angle is going to be equal to 0. Okay, so that's the idea. So this cross product is perpendicular to both U and V. So I forgot to put the arrow here. So therefore, when you do the calculations, the dot product of U dot with U crosses with V is going to be equal to 0 scalar value, right? Because it's the dot product. So here again, U crosses with V will give you a new vector, and this new vector is perpendicular to both U and V. So therefore, when you do U dot with U crosses with V is going to be equal to 0. So the explanation for that is that U crosses with V is perpendicular to U. And for V dot with U cross with V, it's going to be equal to 0 as well, because again, U crosses with V is perpendicular to V. All right. So that's the relationship between cross product and the dot product. Right. So let's do a quick calculation to show that these 2 statements is going to be true. Okay. So let's say you have the dot product. I'm sorry. You have 2 vectors U and V. Can you do this calculation? U dot with U crosses with V and V dot with U crosses with V. So for U crosses with V, right, you're going to form a 2 by 3 matrix 1, 2, -2, and then 3, 0, 1. Okay, and the cross product is going to be equal to the determinant of 2, -2, 0, 1, a negative of the determinant of 1, -2, 3, 1, and then the last one is the determinant of 1 and 1, 2, 3, 0. And the result of the cross product is 2, -7, -6. Now, after doing the cross product, you will form the dot product. U dot with U crosses with V. So U dot with U crosses with V. That is, you do 1, 2, -2 dot with the vector 2, -7, -6. So this gives you 1 times 2 plus 2 times -7. plus -2 times -6, and this has to give you this has to be equal to 0. All right, and you can perform the same calculations in the case of v dotted with u crosses with v. You have 3, 0, 1 dot with 2, -7, -6, and this has to be equal to 0 as well when you perform the dot product. Now, mostly that's it for the property of the cross product, and you learn one technique how to find the value or the vector of the cross product. And I'm going to give you another technique which is more widely used in practice, right? That involve mainly with the determinant without forming any matrix whatsoever. Before doing that, I'm going to touch on the 2x2 determinants and the 3x3 determinant, or determinant of second order and the determinant of third order. So for the 2x2 determinant, you have A, B, C, D like this. The determinant is the product of the main diagonal minus the product of the off diagonal. Right, so we have been doing that quite a lot. And so here, okay. Now for 3x3 determinant, let me do A1, A2, A3, B1, B2, B3, C1, C2, C3. You, of course, can work out the details to calculate the minus and the cofactors, but in here, you can just write out the details of calculation of 3x3 determinant. So I'm going to start with the first column, the first row. The entry is A1. When you choose A1, you delete the corresponding column in the corresponding row, and you're left with A1 times the determinant of B2, B3, C2, C3. Now, when you move on to A2, you have to do negative A2 because this is positive, this is negative, and then later on, when you do A3, you have positive as well. So negative A2 times the determinant of, when you choose A2, remove the corresponding column, remove the corresponding row, and you're left with the determinant of B1, B3, C1, C3, and then the last entry is A3 times B1, the determinant of B1, B2, C1, C2. Okay, so that's how you calculate the 3x3 determinant. Now, when you do the cross product of the two vectors, what you do is you form the following determinant because you need the three components, right? So in the first row is going to be always I, J, and K. So it's slightly different from what we had earlier. Now for the second row, it should be the entry of the vector on the left of the cross product. Right? So this is U1, U2, U3. And for the last row, it's going to be the entry of the second vector in the cross product. V1, V2, V3. And this is the 3x3 determinant, and you're going to perform a 3x3 determinant as follows. So the first part is I, multiply with, so when you do choose I, remove the corresponding column, remove the corresponding row, and you're left with the determinant of U2, U3, V2, V3. For the second component, you do negative J, multiply with the determinant of U1, U3, V1, V3, and then plus K hat times the determinant of U1, U2, V1, V2. So we're going to apply this technique to some example. So in example 6, we're going to calculate the determinant of, the cross product of two vectors using the determinant notation. Okay, so the cross product of U crosses with V is going to be equal to the determinant of I, J, K, -1, 2, 5, and then 4, 0, -3. So here I get I times the determinant of 2, 5, 0, -3. Again, I get this because when I choose I remove the corresponding column and remove the corresponding row, and I left with this entry 2, 5, 0, -3. Now for the second entry, I get minus J multiplied with the determinant of -1, 5, 4, -3 plus K times the determinant of -1, 2, 4, 0. And here I get for J, for the second entry, I remove the corresponding column, remove the corresponding row, and I left with the entry of -1, 5, 4, -3. And for the last entry, I remove the corresponding row, I remove the corresponding column, and I left with -1, 2, 4, 0. And from now, I'm just going to do the 2x2 determinant. So I got -6i minus j times 3 minus 20 plus k times -8, or you can write this as -6i plus 17j minus ak. Right? And this particular form is called the standard unit form. Right? standard unit form, because the representation depends on I, j, and k, or you can write the answer in this form, -6, 17, and -8. So this is just the component form. It's very straightforward calculations to obtain the cross product between two vectors. Now we're going to move on to another example. In example 7, I could ask you to change a little bit here. So instead of a hat, I'm going to use the vector A, vector B, so the cross product between vector A and vector B. The setup for the cross product of two vectors is that of, so A cross with B equal to the determinant of I, j, k, 8, 2, 3, -1, 0, 4. So I got I times 2, 3, 0, 4 minus j times the determinant of 8, 3, -1, 4 plus k times a 2, -1, 0. If you do the 2 by 2 determinant correctly for each component, j and k, you get 8i minus 35j plus 2k. And again, this form is called the standard unit vector form, because the result depends on I, j, and k. Or you can write your result in this form, 8, -35, 2, and this is called the component form.